Every time you send a text message or you upload a photo or you share a video with a family member, that has to go and sit on a server somewhere, inside of a building somewhere. People don't actually realize how reliant they are on this cloud infrastructure.
This is Traceroute, a podcast about the inner workings of our digital world. All the physical stuff that most of us never have to think about. In a world that is increasingly defined by digital, we look at the real people and services building, maintaining, and scaling the internet. I'm your host, Grace Andrews, a technical storyteller at Equinix, the world's digital infrastructure company. In this episode, compute. Amir Michael began working in hardware in the early 2000s. It was his first job out of college.
Found a Craigslist ad for a company that needed someone to repair servers. I'd worked with PCs and I'd built, gaming rigs before in the past. And I said, well, I could fix a server. So I responded to the Craigslist ad, and this company called Google emailed me back. And they said, hey, we liked your resume. Why don't you come in for an interview? And I said, sure, sounds good. Small search engine. Why not?
In the 2 decades since, Michael's made a career of building infrastructure, and he's currently the chief technical evangelist for Lightbit Labs. And over the years, he's worked alongside a number of software engineers.
Good software engineers understand what the hardware is doing underneath. And good hardware engineers understand how the software is utilizing the hardware. And so if you really want to be good at what you do, if you really want to create efficient infrastructure, both hardware and software, you have to have an understanding of both of them.
But even some software engineers don't think much about the physical technology that underlies their work. Michael says many may have never actually been inside a data center, the giant warehouses of chips and processors where the cloud physically exists.
It's out of sight, out of mind. I created a device when I was at Google that lets you write a software algorithm, and it would measure exactly how many kilowatt hours it consumed running on a server. And I could then take that to a software engineer and say, run your algorithm and see how much energy you're using. And that was a concept that was completely new to them, right? And they said, what do you mean? I write software. What do you mean I consume energy? And so they're oftentimes surprised by that.
In the world of the internet, we want things to be invisible. That's even true for a lot of people working in the tech industry. They focus on code and the things they can build online, but not the infrastructure. Michael says, these days, hardware is getting a bigger spotlight because the cloud doesn't run without data centers. And tech giants from Google to Facebook to Apple are investing more in the space.
There's no doubt that the amount of resources they put into the hardware is growing. There are thousands of people at large companies that are driving not only the design of the hardware, but the supply chains behind them as well. And if you just look at the financial reporting from these companies, they spend billions and billions of dollars on infrastructure.
And without that infrastructure, well, no internet.
Hello, my name is Rose Schooler, and I am Corporate Vice President of Data Center Sales at Intel.
She's been with Intel for over 30 years.
We make semiconductors, all kinds of semiconductors. We make semiconductors that store data, and you'll hear products like persistent memory and storage under our Optane brand. We make products that drive connectivity, anything from silicon photonics to Ethernet controllers, a lot of different semiconductors. But we also have a pretty extensive software capability within the company.
The company was founded in 1968, specializing in memory. They moved on to microprocessors, which are central processing areas of computers, often located on just one chip. She's seen hardware grow by leaps and bounds in her career.
I started off as a fab process engineer. That time, our process densities, you think about an analogy, it was like you're laying transistors on the width of a hair. Now we're laying transistors on atoms.
By the early 2000s, they started shifting into a different kind of processing. which led to the networking and storage business, otherwise known as today's internet backbone.
So let's think about the internet. What do? I go back to you move and you process and you store data. And the internet is made up of a bunch of different devices. It could be servers, we're the compute and servers. It could be networking equipment like switches and routers and wireless access infrastructure. Our microprocessors are at the heart of all of those different devices.
Let's slow down a bit here and break down all the building blocks of what we need to get online today.
You've got your silicon, and let's just call it microprocessors, right? And you're going to have them in a PC, you're going to have them in a server, you're going to have it actually in a smartphone, you're going to have it network, you're going to have it in storage. And that's kind of your foundational element. And the more transistors that we put in those, the more features, the more performance, and the more applications that you can run.
Companies take that technology
and they build routers and switches that help build the network. They build storage devices that help manage the data that goes through the network. They build servers that run applications, or the hyperscalers build out clouds to run instances and manage workloads. You have people that are building your wireless infrastructure. So when you want to call your Uber on your cell phone, that all of that compute from the device to the edge, to the network, to the storage, to the cloud, is all built around that foundational microprocessor capability.
So this is the moment when a traditional microprocessor company started caring about the internet. The groundwork was there, but the dawn of cloud computing and the growth of the internet opened the door. They started trying to figure out how their computer technology could support networking, the part of the business that Schooler was running at the time.
And we just said, you know what? There's a bunch of workloads in the network that our architecture isn't necessarily tuned for. Applications, we can run applications all day long. That's what we do on PCs and that's what we do on servers. But there's things like, how do you move packets, which are what carries the data through the internet? And, like when you get a notification on your phone and that you used to get that little circle in the corner of your app, that's part of the control plane function of the network, sending those signals back and forth. And then the wireless access.
Schooler and the company had a vision that they could run a lot of computing functions, the ones necessary for the internet, on their existing architecture.
And it was a giant inflection point for our company, as well as for the companies that serve and help create the internet. And what it really did was bring the computer economies of scale to the network and the internet. And what used to be, an industry that was built on, I'm going to build this piece of silicon with this operating system and this proprietary form factor and this custom software, it just broke wide open.
This means that Intel could start making computers not just for home use, but be integral in making the parts that make up data centers, used for networking, and eventually the cloud.
There was so much cool stuff happening in terms of the next transformation of our industries related to the internet. You had the emergence of the hyperscalers. You had the transformation of networking, storage moving from big fixed function hardware over to software defined.
And it's not just the cloud and networking that have grown. More growth in hardware is on the horizon as things like artificial intelligence, 5G, and edge computing gain traction, and are influencing silicon and chip makers to expand their horizons as well.
But what we're seeing is a big transformation. It's creating new business models, new technology, new approaches to market, new ecosystems. You see the Equinixes of the world. You see managed service providers. You see cloud management platforms. It's like this whole new cool community and ecosystem that's being brought up from these trends that we're seeing in the market around cloudification. And what's driving that? Again, if we go outside in, it's quick access to technology. You can get on your laptop and provision assets real time. So You don't have to go through the whole supply chain. I'm going to order this. They're going to ship it to me. I'm going to land a server in my garage. If I want to do a startup, you just go access technology real time. And I think it's driving new companies, new innovation, and new approaches to the market.
So the cloud physically exists in data centers, and Amir Michael of Lightbit Labs says it was in the early 2000s that these data centers started getting bigger and bigger.
In the early 2000s is when the really large scale, we're talking tens, hundreds of megawatt data center sites really started being planned and started popping up at the time. Google started building their own data centers. Yahoo started building their own data centers.
But for relatively smaller companies, it didn't make sense to build and maintain their own massive data centers.
Running infrastructure can be fairly complex. And if you don't do it well, it's very expensive because you end up being inefficient in how you use your resources. And so that is somewhat disconnected from a product, right? If you're a consumer product, you're streaming videos, that's what you care about. You don't necessarily want to spend engineering resources on managing infrastructure. And so a company that does that well and does that very efficiently, like a cloud service provider, can have an advantage and sell that and make a profit from their efficient management of that infrastructure. And for a company that's trying to build a product, it's a great opportunity for them to be able to focus on their product and not on all the infrastructure that needs to happen on the back end. Not all that different from someone that might be selling a clothing line and they want to focus on the design, but not necessarily on the manufacturing.
So instead of building their own data centers, smaller companies in the early 2000s increasingly turned to other businesses, like Amazon, to meet their cloud and infrastructure needs. So why did the cloud take off? Michael says a major reason was the rise of connectivity-based applications, more people doing things like editing documents on their browsers rather than local devices.
Anything you do on your smartphone today likely goes through some sort of network connection, right? And that really is what spurred the demand for a lot of this data center and remote server infrastructure, really connecting all of these interconnected apps today. If it's from social networking to finance, no one really goes into a bank anymore. Everything's just done over the network, over these cloud resources today. It's how we've become accustomed to getting a lot of work done today. And so you need all that infrastructure to drive that. And I think it's just going to become more and more so in the future as well.
All of this has meant a growing demand for space. The companies maintaining the data centers have had to build and expand. Data centers have been scaling up. And as the industry has matured, there's also been a need to optimize.
The focus has come a lot more on efficiency and how to use as little energy as possible for the surrounding facilities and power distribution and cooling. That's very important.
Tech giants that previously focused on software are more and more interested in the hardware game. Michael says one reason for that is the chance to build hardware tailored to specific applications.
If you have a unique application, if it's, for example, a search application or whatever that is, if you run that on custom hardware, you're going to do that very, very well, very, very quickly, right? If you used a generic server to do that, that server is designed to do many things well, but not necessarily optimized for any one thing. And so that custom architecture gives you the best performance.
Another reason is the scale itself, how much these tech giants are now relying on hardware.
They build so many servers, in some cases, millions of new servers a year are deployed into some of these large companies. You need to have a custom supply chain for that, right? You know what your demand looks like. You can't really rely on a third party for something that is that critical to your business, right? So it's worth it for you to pay for the extra overhead to have that supply chain in place in order to support the scale at which you operate at. You need to have that predictability because you can't afford to not have enough capacity for your service when you're generating so much money off of it.
But innovation in hardware isn't as easy as in software.
Hardware has development cycles that are much longer than software. From the time you make a design decision to the time you see the impact of that design decision can be months, because something physical has to change. A factory has to go and produce this piece of hardware that you designed. You have to receive that and then power it on and test it. And the feedback cycles are much longer. And so the agility that you have with the hardware development process isn't as high as software. You want to make sure that everything is correct before you send it out to manufacture, because you can't just go back and change one line of code and automatically have your product updated that way. You have to go back and change a schematic.
And Michael says further innovation when it comes to data centers is key.
The next thing that's coming up is density. I think people are going to try and use a lot more power and put a lot more resources into smaller spaces, which is a challenge as well. And so there's going to have to be interesting solutions around power distribution and cooling and making that happen as people try and cram more of this compute power into smaller and smaller spaces. And largely that's being driven by wanting to be as close as you can to your end users. And you can't have big, massive, 100-acre data centers near all your users. It's just not going to work, right? And I think that's going to be one shift we're going to see coming in the future too.
The stakes, Michael says, are high.
If we're not able to figure this out, the amount of innovation we have by being able to cram more compute resources into smaller spaces will start to go away. And this pace of innovation that we've had will slow down. And so it's important that we are able to solve that, because innovation is important for our economy, for the creating jobs, for our technology. It's important for the environment to be able to do more with less resources. And so it's something that it's absolutely critical that we figure out.
Ken Patchett has worked on data centers for over 25 years, including stints at Microsoft, Facebook, Google, and Oracle. But he started out as an iron worker.
In fact, I helped build the Canyon Park data center in Bothell, Washington when I was 18 years old. I had no idea what it was.
That early experience took him places he'd never imagined, like the Olympics.
I think it was the 2004 Olympics. I was sitting in front of a SQL server that was hosting the Olympics with an Iridium phone and a radio just in case something happened to that single server. And if I recall, it was a Compact ProLiant 5000 series. So one Compact ProLiant in the box and 4 or 5 SCSI attached drive arrays. At the end of the day, that technology was all-encompassing, it was huge, and it had a huge blast radius. If that server went down, a lot of things would break.
In his years building data centers, he's seen the internet and customer expectations change quickly.
Data and the usage of data has become much like a microwave in a home. It is simply required, it is expected. Most people don't look for it, they don't need it, and they don't really think about it that much until it doesn't work.
Patchett knows just how much it takes to make a data center run well.
The cloud is a combination of data centers of various sizes across the globe that are all connected through network, which is fiber in the ground or satellite systems or some kind of connectivity. And all of that costs a lot of money to do. When we build data centers, a rule of thumb is 4 to 1. So where it costs me $100 to build a data center. It cost me $400 to fill that data center up with servers and computers and the network gear that's necessary to provide this data or this information to an end user. So a lot of people, they just think, oh, if I had a cell phone or if I had a desktop, I would be online. Well, that's not actually true. What's true is you have to have interconnectivity all the way back to where these servers are in these data centers.
When Patchett first started building data centers, redundancy was the goal. So if something broke, there were backups. And companies built data centers that were like bomb-proof bunkers.
I should say, nobody ever got fired for being too safe or for thinking of any crazy corner case that might happen. They used to say, and they still do in large part, don't build a data center near an airport. Don't build it on a curve of a road where a car could come through the window. Don't do this, don't do that. At the end of the day, they were building those rule sets in order to stay up. Uptime was the most important thing, simply because we couldn't handle failure. Software wasn't predictive. Software couldn't readjust. So anything that shook the bones of the internet would cause outages for people around the world.
As they built more data centers and the cloud grew, it made more sense to frame building around resiliency.
Software and hardware have to work together. Data centers fail, data centers break. So as our reliance on this technology or this microwave has grown, so is our need to find ways to keep it available at all times. Because somebody who wakes up in, let's say, Japan in the morning does not really care that the data center of Microsoft in Bothell, Washington had a problem yesterday. It doesn't matter to them. They won't know about it. They won't see it. And they shouldn't have any effect.
It was a maturing of the industry and an understanding of what was really needed to run the internet.
We are aware as an industry that things will fail, that we need to spread them out, we need to distribute them, and we need to have the end users not be impacted by any technological issues that happen. And there's a myriad of them, and they're all physical. A train started on fire in a tunnel. A backhoe cut a fiber line going north and south. That brings technology to a standstill. So building a data center, when we realized that there's a better way to build a data center and it doesn't have to be bomb-proof, would save in some materials costs.
Data centers started redesigning hardware to optimize it for different uses, depending on who's renting the server space. It's kind of like optimizing a race car, stripping out all the parts you don't need to help ensure efficiency.
The industry always goes in two ways. It's like a bow tie. The race car is stripping all the weight out, getting it lightweight, making it go faster and faster and faster. And you want to do that and you got to do that. At the same time, there's somebody that's going to be working on a motor. And that motor is going to be bigger, better, faster. And maybe we have to enhance the frame. Maybe we've got to add a new set of tires. You know, when you think about this, it's kind of like those cool race car guys back in the day on the strip, you know, in Southern California. They're working on a motor. Somebody else is working on a new type of rubber, you know, to stick to the road a little bit better. Again, these companies are all working together and talking together now in such a way as to create infrastructure that is simply better than it has been. I can do more with less. I can focus on my company's workload and type of work because the product set exists out there now that I can buy or build or engineer the thing that is most appropriate for my company's type of workload versus, let's say, company XYZ.
And what that process meant for the data center layouts was,
now we put all compute in one rack, we put all storage in another rack, we have them interconnected through top of network gear, and we're able to leverage resiliency more than redundancy by having all of these things integrated with one another. Let's say on a motherboard, we made them purpose and specific for the work that they were trying to do instead of John Q. Public, who invented a toothbrush and was going to go online with it.
in the quest for more efficiencies, companies also realized that their proprietary hardware didn't always have to be so fortress-like either. They started embracing open hardware projects.
Open Compute really opened the door and said to everybody in the world, Like this data center, this infrastructure space, this server space, this should not be Fight Club. This is better for everybody to come together and figure out how to get bigger, better, and faster and more resilient with these servers and these components. They need to think about a rising tide floats all the boats. Partner with a lot of folks to build an infrastructure that we can then build software products on top of that actually make a better world. We're trying to get more compute units out of every processor. We're always working on the hardware to try and make the hardware take less power and deliver more output or throughput for the workloads that we're working on. These companies sharing their knowledge and their information across the world is allowing us to build bigger, better, faster, cheaper.
Amir Michael says the hardware space has come a long way since the early days of manufacturing transistors and chips.
It started off where you could almost take a warehouse and perhaps seal it off to prevent the amount of dust out there. And you'd buy specific silicon manufacturing pieces of equipment and you'd set them up and you would start manufacturing your own silicon. The barrier to entry was fairly low at that time.
Fast forward a couple decades to today, when materials are smaller and more sensitive to impurities and to dust.
The requirements for building anything become much more stringent. And today, as you hear about in the news all the time, we're talking about billions of dollars to set up a manufacturing site today of highly specialized equipment, highly specialized facilities. And the barrier to entry is much larger now.
Advances in chip production go hand in hand with advances all the way up the stack. And some of the most exciting internet trends on the horizon have hardware to thank. From developments in satellites to artificial intelligence to edge computing and 5G.
Things like 5G, self-driving cars, all of those things that are going to be, game-changing for us. You need to be able to have hardware that can meet the demands of those applications, right? We're asking hardware to do more and more things for us today. We want our cars now to be able to drive around and recognize pedestrians and cyclists and other traffic and stop at red lights and do that all safely. That's a lot of processing power, right? And in the past, you needed a supercomputer to do those things. Now we want to take what a supercomputer was used for and put that in your car. That's pretty cool. And you need really cool hardware for that.
The hardware will need to get there in order for the software to continue to improve.
Lots of companies and economies are now being built on this type of infrastructure. And if it's expensive and cost prohibitive, it limits the growth of our economy and it limits job opportunities for people, right? And so the more efficient we can do it, the more efficiently we can build these bricks that make up our digital economy, the better it is.
And ultimately, the stakes for better hardware are as high as they get, says Ken Patchett.
So one of the most important things that I think about, and even the reason I'm in this career, is that access to information, knowledge, data should be a fundamental human right. And a lot of people in our space say, well, it doesn't matter, nobody died. Well, they do. There's somebody right now in an underserved market in some part of the world who's trying to figure out if their child has dysentery or not. And access to that information and that knowledge is the reason that I got into this space, so that we could build infrastructure such that other people around the world would have access to this and they could have a better life. So we need to keep that in mind. This is real stuff, folks.
This has been Traceroute, a 7-part series about the inner workings of our digital world. From Equinix, the world's digital infrastructure company. To find more from the people behind the internet, check out Origins.dev for an up-close and personal look at our digital world through a creative lens. And if you're ready to dive in deeper, visit youtube.com/Equinix developers for developer-led, live-streamed technical content. Thanks for listening to Traceroute, an Equinix production. Our theme music is by Ty Gibbons. This series was produced by Rococo Punch. Be sure to subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can learn more by heading to metal.equinix.com/traceroute. Want to get in touch? Reach out to us at metal.equinix.com and make sure to leave us a review and tell us what you think. I'm your host, Grace Andrews. Thanks for listening.